Okay, some solved problems for chapter 42. We had two hydrogens that are bonded together with a covalent bond to form H2. We know that this has an energy of about 4.5 electron volts. How much energy does it take to break this thing apart? What wavelength of light would we need for this to happen? Well, we know that E is going to be equal to H multiplied by C divided by lambda. So lambda is going to be equal to HC divided by E. And so this guy right here is going to be equal to 4.136 times 10 to the negative 15th. Again, that is in electron volts seconds, multiplied by 3 times 10 to the 8th, divided by 4.48 electron volts. You go ahead and you type all that in, and we're going to get about 277 nanometers. Keep in mind that we could have wavelengths that were smaller than this, smaller wavelength, more energy, and that would break that H2 bond apart. Okay, now let's get some practice using rotating molecules. So we're going to have a lithium bonded to some hydrogen, and we're going to kind of set this thing rotating. And what we kind of know is we know the masses of the lithium, the mass of hydrogen, and we also know that the separation distance. And we're looking for the energy difference between the L is equal to 3 and L is equal to 4 rotational levels. So this is going to be what we're looking at. We do need to know the moment of inertia for this. And so that's going to be the moment, that's going to be the reduced mass multiplied by the distance of separation squared, which they gave us, 0.159 nanometers. So first thing we're going to do is we're going to use this guy right over there, as well as the masses of the lithium and the hydrogen. And I'm going to spare you me typing all that in. The reduced mass is going to work itself out to be 1.461 times 10 to the negative 27 kilograms. And that's going to let us calculate this guy right there. It's going to be equal to this multiplied by this squared. Make sure you put that in nanometers, or put that nanometers to meters, and we're going to work out to be 3.694 times 10 to the negative 47th with a unit of kilogram multiplied by square meter. Now we can go ahead and calculate our energy levels, and we can say that the energy level for L is equal to 3 is going to be equal to 3 times 3 plus 1, which is going to be 4, multiplied by h bar squared divided by 2 times I. So that's going to be 12 divided by 2, that's going to be 6. So it's going to be equal to 6 h bar squared divided by 2I. And the energy level for my L is equal to 4. That's going to be equal to 4 times 5 times h bar squared divided by 2 times I. So that's going to be 20 divided by 2. That's going to be 10 h bar squared divided by 2I. Now, pretty straightforward. Delta E is going to be equal to E4 minus E3, which is, I've got my little 2 right over there, sorry about that. So that's going to be 6 minus 10. That should be equal to 4 h bar squared divided by I. And now I know all these guys. I can take this guy, plug it in right there. H bar squared is just going to be h divided by 2 pi. And want to use the joule version of it, it's going to work its way out to be equal to 1.2 times 10 to the negative 21 joules. Or you could do the electron volt version of h bar, and you're going to get 7.49 times 10 to the negative 3 electron volts. Now for part B, we're interested in the wavelength. And so what we're going to do is we're going to say, okay, same as before, wavelength is going to be equal to h multiplied by c divided by delta E. And let's see, this is going to, I'll do the electron volt version, 4.136 times 10 to the negative 15 electron volts multiplied by 3 times 10 to the 8th divided by 7.49 times 10 to the negative 3. And we're going to get 166 times 10 to the minus 6 meters, or 166 microns. Okay, now for problem number 16. Actually, I'm just going to do 16 part A. I'll let you do the other ones if you want to for practice. We're taking a look at CO, and we worked examples 42.2 and 42.3 and learned a little bit about their vibrational and rotational energies. We know that we can write their rotational energies like that, and the vibrational energies like this. And in 42.2, we learned that h bar squared over 2I for CO was equal to this teeny tiny amount of energy, and the rotational and the vibrational energies gave us h bar omega is equal to 0.269. So what this kind of says is the vibrational one is going to win when it comes to the wavelength as well as the energies. So let's go ahead and also kind of say that the total energy is going to be equal to the energy of the rotation plus the energy of the vibration. Again, L's and N's are going to tell you that. And so the energy when n is equal to 0 and L is equal to 1, so that's going to be 0 times 1, is going to be equal to 1/2 h bar omega. I just set n is equal to 0. And then I'm going to add on my rotational. That's going to be 2 h bar squared, or h bar squared divided by 2 times I, just using this guy right over here. And then my energy when n is equal to 1 and L is equal to 2 is going to be now 3/2 h bar multiplied by omega plus 6 multiplied by h bar squared divided by 2 times I. And now my delta energy is going to be the final minus the initial, and you can convince yourself that's just going to boil down to h bar multiplied by omega plus 4 h bar squared divided by 2 times I. And now I know what these guys are from my examples, and so the change in energy is going to be equal to 0.27, and that's 2.700 electron volts. So that's going to be the energy that's associated with that. And again, most of the energy comes from the vibrational, very little from the rotational. I'm going to do the same thing that I said before. Lambda is going to be equal to hc divided by my change in energy. And this guy is going to go ahead and work itself out to be about 4.592 microns, or micrometers. Okay, now we have a silicon photocell, and something that we notice is when we shine some light on it that it's going to have some minimum wavelength, and it's going to be 1.1 micrometers. And energies that are associated with that is going to be essentially the energy of the band gap. And we could talk about higher frequency light. That would be a lower wavelength. That would be able to get some voltage across this photocell. But the wavelengths that are smaller than that aren't going to have enough energy, so we're not going to be able to pick those electrons from the valence band up to the conduction band. So pretty straightforward. We know that the delta E is going to be equal to hc divided by wavelength, and I'm going to want my answer in electron volts, so I'm going to use the 4.136 times 10 to the negative 15 electron volt seconds multiplied by C. It's going to be 3 times 10 to the 8th. Now 1.11 times 10 to the minus 6, and that tells us that our energy gap is going to be equal to 1.12 electron volts. Now, why is pure silicon opaque? Well, if you think about it, this is in the infrared, and visible light is going to have a lower wavelength. Lower wavelength means more energy, and so visible light would be able to excite this guy, and it would be absorbed. So we're not going to be able to see through pure silicon. And last but not least, let's get some practice using the Fermi-Dirac distribution. Here we have some germanium, and we know what its temperature is, and we know that we're going to have our conduction band, and we're going to have our valence band, and we know the probability that an electron is in the bottom of the conduction band, so we know the probability that an electron is going to be right there. What we're interested in is we're interested in what is the Fermi level relative to the conduction band, so we're interested in E minus EF is equal to what? So what we can kind of do is we can kind of say, okay, from the Fermi-Dirac distribution, we do know that we could say E to the E minus EF divided by KT, is going to be equal to 1 divided by this probability plus 1. And we know what the probability in it is. It was 4.4 times 10 to the minus 4th. And so that's going to be equal to 2.272 times 10 to the 3 when you go ahead and you plug that guy in right down there. And now we can take the natural log of both sides, and we could say that E minus E sub f, which is what we're interested in, is going to be equal to k multiplied by t multiplied now by the natural log of 2.272 times 10 to the 3. And we can work this guy in joules, or we can work it in electron volts. I'll leave that guy up to you. But we know that the temperature is going to be 300 Kelvin, and I'll prefer to work this in electron volts. It's going to be 0.2 eV.